Hello, today we're going to do a molar volume of a gas lab using this reaction up here at the top. Solid magnesium is going to react with hydrochloric acid to form magnesium chloride and hydrogen gas. The first thing I want to do is gather some kind of reference information. I'll collect the atmospheric pressure or the room pressure and the room temperature. I like to use this as an opportunity to introduce students to some of the probes that we have. So I have the LabQuest 3 here with a barometer and a temperature probe. So our atmospheric pressure is 0.997 atm and temperature is 21.2 degrees Celsius. Now, if you don't have probes like this lab still works great. You can look up the atmospheric pressure where you are just online. And you can use like your classroom thermostat or a regular old alcohol thermometer to figure out the room temperature. Once you have the room temperature, you can look up, using a table of values, the water vapor pressure at that temperature. So at 21 degrees Celsius, the water vapor pressure is 18.7 millimeters of mercury, which in ATM is 0.0246. So this is an excellent lab for us to look at Dalton's law. When we go to collect this gas, we're going to be collecting it over water. So you're in your tube, your collection tube, you'll have water and you'll have your hydrogen gas, but you will also have some water vapor because some of this water will evaporate. Not a lot, but it's dependent on the temperature. Higher temperatures, more will evaporate. So that's why we look up the water vapor pressure. So that means the total pressure in here is going to be equal to the pressure of the water plus the pressure of the hydrogen. And our total pressure will be equal to the atmospheric pressure, which is 0.997. Our water vapor pressure we found was 0.0246. We can solve to find the dry hydrogen gas pressure. You just subtract. So 0.997 minus 0.0246, I got 0.972 is my dry pressure. Okay, so I'm going to get rid of this for the moment, and that's an ATM. Now, for this lab, we want magnesium to be our limiting reactant. So we want to use just a small amount of magnesium and an excess of the hydrochloric acid. You should get about 0.02 grams of magnesium for this if you're using 1 molar HCl. What I do is I have students use just like benchtop digital balances to get close to 0.02, and then they take their piece of magnesium up to the analytical balance to get the exact mass. Okay, so using the analytical balance for this small piece of magnesium, I found that the mass was 0.0292 grams, which is a little bit higher than we were expecting, but it's still perfectly in range for this kind of lab. Also, if your balances only go to the hundredths place, you should still be fine for this lab, but you could talk about that as like a source of potential error that you might not have the precision to be able to calculate it to the correct level. Okay, so for the actual lab setup, you need a UDometer, which is basically just like a graduated tube. I have a bowl of just tap water. I have this stopper, which is just like a rubber stopper with a hole in it, and I have some copper wire. And I've attached just a piece of like sewing thread to it. The copper wire is good because it doesn't react, and then the sewing thread is going to attach the magnesium. What we're going to need to do is then take the UDometer. You're going to flip it upside down. You want to put about 7 or 8 milliliters of 1 molar hydrochloric acid in the bottom. And then we're going to slowly add deionized water at a slant. So the water is less dense, so it's going to, we really just don't want it to mix. So you want the water to fill up all of the way to the very, very top. So you'll have acid and then water. So I've tied the magnesium metal in the top part of that copper wire, and I've put 7 or 8 milliliters of hydrochloric acid It doesn't matter the exact amount, remember, because it's our excess reagent. And then I filled the rest of this with deionized water. Now I'm going to submerge this into the water and get a really, really nice and tight seal. And then I'm going to cover it with my thumb and submerge it in the bucket of just tap water. And make sure it's completely submerged before you remove your thumb. And then you can secure it with the burette clamp. You want to make sure you leave just a little bit of space, so that way the water can still get in or out for the water displacement. And very slowly that acid is going to sink down, and you will start to see this bubble and form hydrogen gas as the acid meets the magnesium. You'll know that the reaction is complete when you stop seeing the bubbles, and most of the magnesium should be reacting. Now, in theory, all of it would react because it's our limiting reagent, but in practice, you're not going to see 100% of it. But really, once the bubbles stop forming, that's going to show you that the reaction has finished. All right, now that the bubbles have stopped forming, I'm going to go ahead and take the eudiometer out of the clamp. I'm going to use my thumb to plug up the bottom of the eudiometer to make sure there's no loss of any water, and transfer it over into this really large graduated cylinder. The reason why I want to do that is to make sure that the level of the water inside the eudiometer is the same as the level of the water in the graduated cylinder. And the goal of that is to make sure that the pressure that we measured for the atmospheric pressure is the same as the pressure inside the eudiometer. And we can do that by matching the water levels. So let me show you how we do that. Take this out. I'm going to use my thumb to stop her up. You might want to tap on it a little bit too, because there's bubbles along the outside that haven't made it to the top. And then grab it with your thumb, and we're going to transfer it up into this big graduated cylinder. And don't let go until it gets in the water. And then you want to equalize the water level inside and the water level outside, so we know what the pressure is. And once it's equal, you can record the volume in milliliters. And I'm measuring a volume of, looks like 31.9 milliliters, maybe 31.95 milliliters when those water levels are equal. All right, so now let's look at the calculations for this lab. The first thing you want to do, and you can even do it very early in the lab, is have students calculate the moles of magnesium just using the molar mass. Now in reality, some of that magnesium is going to be magnesium oxide, because the outside of it will oxidize fairly readily in air. But we're just going to assume that it's entirely magnesium. And when you divide by the molar mass there, you're going to get 0.00120 moles of magnesium. And for every 1 mole of magnesium that reacts, 1 mole of hydrogen gas is produced, which is nice. So we have the same moles for hydrogen. And we already found the pressure of the dry hydrogen gas was 0.972 atm. And then in the eudiometer, we collected 31.9 milliliters, which is the same thing as 0.0319 liters. Okay, so now some teachers will stop at this point and have students use PivNert. So plug in the pressure of the dry hydrogen, plug in the volume in liters, plug in the moles of hydrogen, and plug in the temperature in Kelvin, and solve for an experimental value of the gas constant. Then you do your experimental and the published value, the 0.08206, and to find your percent error for the lab. So that's one way to finish out this lab. I like to go ahead and find the actual molar volume and do it that way. Because instead of using Pivnert, which we use all the time, you're going to need to then use the combined gas law. Right. So the molar volume, the published molar volume, is always at STP. So if we need to use the combined gas law, P1 V1 over T1 equals P2 V2 over T2, plug in the values that we have and solve for the experimental molar volume at STP. So let me go ahead and plug those values in. Our pressure of the dry hydrogen was 0.972 atm. The volume in liters, 0.0319. The temperature was at 21.2 degrees Celsius. So in Kelvin, that was 294.35 Kelvin. Now at STP, we assume standard pressure is 1 atm. We're looking for the volume, and the standard temperature is 273.15 Kelvin. So if you solve all of that, you will get the volume V2 is 0.0288 liters. That is our experimental volume at STP. I'm going to move this away so we can record this properly. 0.0288 liters at STP. Now to find the molar volume, you need to take the liters that we just found and divide by the moles of hydrogen that we had. 0.00120 moles, and to get our experimental molar volume was 24.0 liters per mole. And of course the theoretical, the published value is 22.4. I'm using this value because that is still the published value on the AP Chemistry formula sheet as of the 2024 published formula sheet is 22.4, so there's that. And then we're going to use that value to find the percent error. So percent error, we're going to do the 24, the experimental, minus the theoretical, all over the theoretical, times 100, and I got a 7.04% error, which is pretty good. And students usually get a fairly low percent error for this lab, provided they get through the calculations pretty readily. Now, two really common sources of error for this lab. If students allow bubbles to get into the eudiometer, either when they're first putting the magnesium metal up inside the eudiometer, they could get bubbles inside then. That would increase your measured volume. Or when you're transferring the eudiometer to the large graduated cylinder. Either way, you could get extra volume than you would expect, and increasing the volume that you're measuring would also increase your calculated experimental molar volume. Another common source of error is if the reaction did not go to completion. So if you still had some unreacted magnesium left over, that means not enough H2 was produced. So that would mean your volume would be lower than expected, and your experimental molar volume would be lower than expected as well.